Case 1, two distinct real roots. Welcome back, everyone. Before we dive into today's new topic, let's quickly recap what we covered in our previous lesson. We introduced a very powerful tool called the discriminant, which we denote by the capital letter D, and it is calculated using the formula b squared minus 4ac. Now, why is this formula so important? Well, the value of this discriminant acts as the deciding factor in determining the nature of the roots for any quadratic equation in the form of a x squared plus bx plus c equals 0. In other words, it tells us exactly what kind of answers we should expect to find. In this specific subsection, we are going to zoom in and focus on the very first scenario, the case where the discriminant is a positive number. We'll explore exactly why a positive value leads to two different solutions and what that looks like in practice. Understanding the concept, take a look at the first point here. When the discriminant, which we denote as d, is greater than 0, it means the entire expression sitting under the square root in our quadratic formula is a positive real number. Let's bring that formula back into view. As you remember, the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, if the value of b squared minus 4ac is greater than 0, then the square root of b squared minus 4ac will result in a real number that isn't 0. This is the crucial part. Because of that plus-minus sign in the middle of the formula, we can't just perform one calculation. We are actually required to perform two separate operations, one where we add that square root value and another where we subtract it. Because we are doing these two different operations, it leads us to two separate and distinct values for x, our first root, which we can call x sub 1, is calculated as negative b plus the square root of b squared minus 4ac, all divided by 2a, our second root, or x sub 2, is calculated as negative b minus the square root of b squared minus 4ac, all divided by 2a. Think about the logic here. Since we are adding a positive value in the first case and subtracting that same positive value in the second, the results for x sub 1 and x sub 2 will always be different numbers. And that is exactly why, in this specific scenario, we say the equation has two distinct real roots. Now that we've recalled what the discriminant is from our previous slide, let's dive into the why behind this first case. In the next slide, I'll show you a clear, step-by-step process you can use to identify these roots every single time. Step-by-step process to identify distinct roots. Now that we understand the theory behind why a positive discriminant leads to two different answers, let's look at a practical, step-by-step workflow you can use every time you encounter a quadratic equation. This will help you stay organized and avoid errors. First, your very first step is to check the standard form. Before you do any math, make sure your equation is written as a x squared plus bx plus c equals 0. If there are numbers on the right side of the equals sign, move them over to the left first. Second, once you have it in standard form, identify your coefficients. This simply means clearly labeling your values for a b and c. I highly recommend writing them down on the side of your paper so you don't lose track of them. Third, calculate the discriminant. Take those values you just identified and substitute them into the formula. D equals b squared minus 4, c. This is where you'll do the actual arithmetic. Finally, you must analyze the result. This is the most important part for our current topic. If your calculated value for d is greater than 0, then you have confirmed that the equation has two distinct real roots. However, if your result is less than or equal to 0, then this specific case we are studying today does not apply, and you'll be looking at a different type of root. In the next slide, we're going to put this exact four-step process into action using a real-world physics example involving a thrown ball. Real-world example, projectile motion. Now that we have gone through the theoretical steps for identifying roots, let's see how this actually applies to a real-world scenario. We'll look at a concept from physics called projectile motion. You see, in physics, the height of an object thrown into the air can often be modeled using a quadratic equation. To make this concrete, let's suppose a ball is thrown upwards, and our goal is to find the specific times, which we'll call t, at which the ball reaches a height of exactly 10 meters. The situation is modeled by the equation negative 5t squared plus 20t plus 2 equals 10. Now, remember the step-by-step process we just discussed on the previous slide. We can't find the discriminant until the equation is in standard form. So, step 1, convert to standard form. We need to set the equation to 0, so we'll subtract 10 from both sides. This gives us negative 5t squared plus 20t minus 8 equals 0. Step 2, identify the coefficients. Looking at our new equation, we can see that it equals negative 5, b equals 20, and c equals negative 8. Step 3, calculate the discriminant. We'll use our formula, d equals b squared minus for a c plugging in our values, we get d equals 20 squared minus 4 times negative 5 times negative 8. When we calculate that, 20 squared is 400, and 4 times negative 5 times negative 8 gives us 160. So 400 minus 160 leaves us with a discriminant of 240. Step 4, analyze the result. Since our discriminant, d, is 240, which is clearly greater than 0, we can conclude that the equation has two distinct real roots. But what does this actually mean in the real world? This is the physical interpretation. In this context, those two distinct roots represent two different moments in time when the ball is at exactly 10 meters. The first time is while the ball is ascending or going up, and the second time is while the ball is descending or coming back down. Before we move on to some common pitfalls to watch out for, keep this visual in mind. The two roots are simply the 2 points where the ball's path hits that 10-meter mark. Common mistakes to avoid. First, let's talk about sign errors in the discriminant. This is perhaps the most frequent mistake students make. When you are calculating the discriminant, you must be extremely careful with negative signs. For instance, if either a or a is a negative number, the term negative for a c might actually become a positive value because of the double negative. To prevent this, I highly recommend that you always use parentheses whenever you substitute negative values into the formula. Instead of writing it loosely, write it as d equals open parenthesis b close parenthesis squared minus 4 open parenthesis, a close parenthesis open parenthesis c close parenthesis. This keeps your work organized and prevents errors. Second, be very careful when squaring negative numbers. It is a fundamental rule in algebra that b squared will always be a non-negative number, regardless of whether b is positive or negative. A common error is to say that if b equals negative 5, then b squared is negative 25. However, remember that negative 5 squared is actually positive 25. Always treat the square of a real number as a positive result. Finally, do not confuse the term distinct with equal. As we discussed in our earlier slides, distinct specifically means that the two roots are different, separate numbers. If your calculation results in the discriminant being exactly equal to 0, the roots are still real, but they are not distinct. They are identical. We only use the term two distinct real roots when the discriminant is strictly greater than 0. Now, before we wrap up our lesson and look at the final summary, I want to pause and discuss some common pitfalls. Even if you understand the concept of the discriminant, it is very easy to make small computational errors that lead to the wrong conclusion. Keep these points in mind as we move to our final slide for the key takeaways. Key takeaways. All right, we have reached the end of this lesson. Let's take a moment to wrap everything up by reviewing our key takeaways so you can ensure you've mastered this concept. First, let's revisit the fundamental condition. Remember, a quadratic equation where a x squared plus bx plus c equals 0 will have two distinct real roots if, and only if, the discriminant, which is b squared minus 4ac, is greater than 0. This is the golden rule we've been using throughout the lesson to identify this specific case. Second, let's look at the mathematical reason why this happens. As we discussed when looking at the quadratic formula, The presence of that plus-minus sign in front of the square root of the discriminant is what creates the split. Because we are adding a positive value in one calculation and subtracting that same value in the other, the formula naturally produces two different numerical values for x. Finally, I want you to visualize this geometrically. If you were to plot this quadratic equation on a coordinate plane, the graph would form a parabola. Because we have two distinct real roots, this parabola will cross the x-axis at exactly two different points. These x-intercepts are precisely the two roots we calculated. Keep these 3 points in mind: the condition, the algebraic result, and the graphical meaning, and you will have a complete understanding of case 1.